Hi, welcome to CockroachDB Bytes. I'm John St. John. I'm your host, and today I put together a few slides to talk about high availability in Cockroach. Let's go to it. All right. So first of all, I just want to say that high availability is really fundamental to how CockroachDB is designed and architected, right? It applies to many different types of database system operations that might require downtime in traditional systems. For example, schema changes, backups, upgrades, and different types of failures. So I want to look at more closely at how CockroachDB maintains high availability during two different scenarios, upgrades and failures. But before we get started, I want to identify the key concepts that relate to high availability, starting with a range, which we've talked about in the past. A range is a contiguous chunk of data that's typically less than 512 megabytes or up to 512 megabytes in size. And each range has a number of replicas, which are copies of the data that exist on different nodes. So each group of replicas has one replica designated as the leaseholder or leader at any given time. And that leaseholder coordinates writes and reads, and most of the reads. All the other replicas in the group are followers, and they maintain a consistent state with the leaseholders and can take over that responsibility at any time through a lease transfer. Finally, if we ever fall below the configured number of replicas, new replicas can be created using a process called upreplication, and we'll cover this when we talk about failure scenarios. So for our upgrade example, we're going to use a 4-node cluster, which is a little bit atypical for a Cockroach cluster. Typically, we would choose an odd number, which works well with Raft consensus to achieve quorum. But 4 nodes fits kind of nice on the page, so we're going to go with it, and it's sufficient to demonstrate high availability. So on the left side, we have a 4-node cluster running 22.2.7. Then the cluster has 2 ranges and 3 replicas for each range. Because we have 4 nodes and 3 replicas, not every node has a replica from every range, and that's typical of a running cluster. So the leaseholder for each replica is shown in bold and solid lines, and the followers are shown in non-bold dotted lines. For example, node 1 is the leaseholder for range 1, but it's a follower for range 2. So to start the upgrade process, a node is chosen, could be any node. And then before actually upgrading Cockroach, the node is drained. And draining is just a process that gives the node time to finish any active work, such as a running transaction, and to transfer leases away from itself. So on the right side, we can see the state when node 1 has been drained and is in the upgrade process. And the lease for range 1 is transferred to a follower replica, in this case on node 3. And then when the drain is finished, the Cockroach process is shut down, and the binary is replaced with the upgraded version. And then the node is started back up. And when it starts up again, it rejoins the cluster. So on the next slide, on the left side, we can see what happens after node 1 is upgraded and rejoins the cluster. So it's now running 22.2.8, and the lease for range 1 is transferred back to the node. At this point, the cluster is running in a mixed state, or mixed version state, and this is okay in Cockroach, even up to a single major version. And it's actually how we do rolling upgrades, where each node is upgraded at the same time without affecting availability. On the right side, we see the next step in the upgrade process, which, as you might guess, is node 2 getting drained, which also will trigger the lease transfer away. We can upgrade node 2, and then it rejoins the cluster, and leases are transferred back. So one thing to note is that as a distributed system, there's no central coordinator of where leases should be at a given time. So it's a bit of a simplification just to say the leases get transferred out and get transferred back. lease transfers are a normal part of cluster operation, and typically they would be used to balance leases and replicas across the cluster. So when the node joins back in, it's likely that it'll receive, because it has the replicas that it previously had, it's likely that it'll get lease transferred back for most, if not all, of those replicas. So this process will occur until all the clusters in the node are upgraded, and this applies to both patch upgrades and major upgrades. So that's how we maintain availability in an upgrade scenario. So how about a node failure scenario? Well, on the left side, we have a steady state running cluster, similar to what we had before. But on the right side, we see that we have a failed node, and we didn't have a chance to gracefully drain that node. So there's really two types of lease transfers. There's cooperative ones that happen when nodes communicate with each other and are able to cooperatively transfer the lease. And then there's uncooperative, and that would be the case where you have a sudden failure. So in the background, the nodes in a cluster are constantly communicating, and the replicas for a range will communicate the leaseholder leader status. If a leader or leaseholder suddenly disappears, then there's what we call a leader election, and that's part of the Raft consensus protocol. So this leader election is essentially all of the nodes trying to become the leader at once. So the first node that claims leadership will become the leaseholder and become a leader. So we can see the results on the right side of the failure, where node 3 has won leader election for range 1, and node 2 has won the leader election for range 2. Actually, it already had leader, so really we're just talking about the leader for range 1 going to node 3. And just to note here, we're looking at node failure, but Cockroach by default tolerates node and availability zone failures. When we are working with multi-region clusters can also be configured to tolerate region failures. Finally, I just want to look at the case of a permanent node loss. So if the node's down for more than 5 minutes, the cluster will start to upreplicate to ensure the sufficient number of replicas. You'll notice that on the previous slide, we actually had under-replicated ranges where we had only 2 out of the 3 available. So after 5 minutes, if the node's not back online, then we'll start the upreplication process. And during that process, snapshots of existing ranges are sent to other nodes, and this is pictured on the left. Finally, if the node is permanently lost, it would be typical to spin up a new node and add it to the cluster. And as soon as it's added, the cluster will recognize that that node doesn't have replicas and ranges, and it will upreplicate and transfer leases to rebalance, to automatically rebalance to that node. So that is what I have for just a small bite of high availability in Cockroach. There's a lot of different aspects of it, a lot more technical detail, but this is just a high level to give you a bit of an understanding about how Cockroach is designed and architected for high availability and how it achieves it. Thank you for joining, and hope you have a wonderful day.